In this video, we're going to take a look at another test that can be applied to series with positive terms. And this test is called the ratio test, and you'll see why in a second. And, we tend to look at these tests towards the end of this set of tests because these are sometimes considered like the last resort. So you want to look for easier patterns, things like geometric and telescoping. But if all those fail, right? If all those fail, and the series, the terms of the series just seem a little bit more complicated, things that we can't integrate, for instance, and apply our integral test, then we're going to resort to the ratio test. And then there's another one that's very similar to this that will be discussed in the next video. But this one is the ratio test. Let's see if we can describe what this test does. Right? We're going to look at the description of the test. There's a simple theorem, and then we'll look at a couple examples. Now, this one I will not present the proof. It's a little advanced. Some of the concepts that are in there, not terribly difficult, but it's just usually a proof like this is reserved for like an advanced calculus course or a real analysis course, right? Which actually we do offer here. All right, so let's go ahead and look at the ratio test, and I'm going to state the theorem. Right, so this is the ratio test. And remember, this one, like all our recent ones, are exclusively for series with positive terms. So let's write down our series. So let a sub k, and then again, I'm not going to specify whether it starts from 1 or 0. That's kind of irrelevant when you're talking about just convergence, but let this be a series with positive terms, right? And let's define a new quantity. We're going to call this R. So let's define R to be a certain limit. I know we've been using a lot of limits recently. So let's say this is R is defined as the limit as k goes to infinity of something. And now we're going to write down what that thing is. Now the reason why it's called a ratio test is we're going to take a limit of this ratio. Right? This is the ratio of a sub k plus 1 divided by a sub k. So this basically, it's saying take your general next term and divide it by your general previous term, and then take the limit of that, and we're going to call that limit R. And then based on the value of R, we may or may not be able to make a conclusion. All right, so let's say we have this. So our first conclusion is this. So part A says if your R comes out to be less than 1, right, if that ratio, that limit of the ratios is less than 1, then the series converges. All right, that's good. If your R is greater than 1, then the series diverges. And that's pretty good too. Now, unfortunately, there is a case where the test essentially fails, right? And that's when, and you might be able to guess it, if your R is equal to 1, then the series may or may not converge. In other words, the test fails, and in that case, we try another test, right? Right, and that's the idea. Simple setup. Really, there's a ratio. Now it's simple, and some of the algebra might be involved, but to get a look at that, the algebra that may be involved, let's go ahead and do a couple examples. Right? All right, so we're gonna look at some examples of this, and I'm just going to write down the series, and each of them we're going to apply this ratio test, and then we're going to see what the conclusion, if there is a conclusion at all. All right, so example A, here's our series. Let's say k goes from 1 to infinity, and we have k over 4 to the k. Right? Now, we look at this, and this summand is not terribly complicated, right? And maybe one of our previous tests would work, but obviously what we want to try to do here is illustrate the ratio test. So what I'm going to do right off, in fact, I'm going to do this below. I'm just going to write down everything that we need to apply the ratio test. So we're going to identify that the terms of our series, they look like this. It's k over 4 to the k. And then the ratio test also needs us to take a look at the next term. So what term would come after this? Right? Well, this subscript of k plus 1 is just telling us that we would replace all the k's in the general term with k plus 1 to get the general but successive term. So the term that would come after this one, it would be k plus 1, basically the next integer there, and then divided by 4 to the k plus 1, again the next integer there. All right, so we have these. Now let's set up the ratio. So again, I like to do all the algebra, all that setup before I even consider doing a limit. Sometimes when you try to do it all together, things just get muddled, and that's why I think it's important to know the sequence of steps in all these different solutions. All right, so we're going to take this term and divide it by this term. So I'm going to write down the successive term. It looks like this. And think about what this division is saying. We're literally dividing. I'm going to use my division symbol there, dividing by the k over 4 to the k, right? Well, let's work with what we know about exponents and fractions. So that numerator can't be factored anymore. This denominator can be factored as 4 to the k times 4 to the 1. I'll put a 1 there just for emphasis. And then I know how to divide by a fraction. I'm going to multiply by its reciprocal. So I'm going to multiply by 4 to the k over k. And then as soon as I do that, I realize that I can get rid of the 4 to the k. So that completely goes. And then what are we left with? We have k plus 1 in the numerator, and then in the denominator we have just a 4k. And that's our ratio. This is our ratio of successive terms. And before we move to the next step, because we're very close to being done with this, I do want to make a point that let's say you didn't even really think about all the other tests. You just kind of jumped into the ratio test. It's the most recent thing you've learned, and you come out with this expression. And notice that this ratio is not a constant. So because this is not constant, then that implies that our original series is not geometric. So this implies, in fact, let me write it here, this implies that our series is not geometric. If the ratio of the successive terms came out to be a constant, like 1/4, for instance, or a half, or 8, right? If that ratio came out to be a constant, then that would have been a clue to say, hey, this was actually geometric, and you could have done this an easier way, right? The ones where the ratio comes out to be, again, let me just throw a couple buzzwords out there. This type of function, we've seen it many times. It's a rational function. It's basically a ratio of polynomials. Whenever your ratio of successive terms comes out to be a rational function that's not a constant, then we call the series hypergeometric, right? So just to kind of mention that there, because sometimes there are clues that can come up in a solution that could lead you to think, hey, there is an easier way to do this, right? But that's not the case here. So we don't have a geometric series. we have, in fact, a hypergeometric series, and then we're now going to compute the r, right? So this important number r, so remember how r is defined. It is the limit as k goes to infinity of that ratio, k plus 1 over 4k, right? Now, if you look at this right away, this is an indeterminate form, right? So infinity over infinity, and we have lots of ways that we can approach this. You know, just for fun, I'm going to apply L'Hopital's. So if I apply L'Hopital's here, because it does apply, because it's an infinity over infinity case, I'm going to take the derivative of the top. That's just going to give me 1. And take the derivative of the bottom. That's going to give me 4. The limit of a constant is that constant. That's one of our wonderful limit properties, and there you go. So we've computed r, and it comes out to be 1/4, right? So what it says is, for a specific pair of successive terms, this would be the ratio, right? However, in a limiting sense, if we look at that ratio as the number, as we go further and further out in that series, that ratio gets closer and closer to 1/4. So it's almost saying that in some sense, towards the end of the series, it kind of acts like a geometric series with a r of 1/4. And if we then apply our knowledge of the geometric series, the conclusion, and this is what the theorem is saying, because our r is less than 1, so here's our conclusion. So since this ratio in a limiting sense is less than 1, the series converges, right? And that's it. We don't know what it converges to. It converges to some number, right? And then there are fancier techniques in some cases where we can figure out what that number is. But all we know is that there is a number, and if I write out these terms, so here I'm going to write out the terms unsimplified. This is 1 times 4 to the 1 plus, 1 divided by 4 to the 1, 2 divided by 4 squared, and then plus 3 divided by 4 cubed, and then 4 divided by 4 to the 4th. I'll do one more just for fun, 5 over 4 to the 5th, and so on. So what happens is if we were to continue adding up terms that follow this pattern, our terms, our sum, right, would get closer and closer to some number. We just don't know what that number is, right? So that's part A. Let's take a look at another example illustrating the ratio test. I'm going to include a function. So I'm going to include a function that oftentimes is a clue that you should use the ratio test. And here it is. So we have a series that goes from 1 to infinity, and here is the summand. It's k to the k over k exclamation mark. And this exclamation mark represents a function that we call a factorial function. Right? And if you haven't used the factorial function, here's just a very quick intro to what it is. We define the factorial functions over the integers, meaning that it's a function that we can only apply to integers. There are fancier ways to extend it, but this is how the factorial function is defined. You take whatever that integer is, and then you multiply all the previous integers, meaning k minus 1, k minus 2, all the way down to 2 times 1, right? And it's just this big product, right? And the product starts with whatever this integer is, and then you multiply all the integers prior to that down to 1, and you'll get it. You know, so for example, if you wanted to compute 5 factorial, it will be 5 times 4 times 3 times 2 times 1, and that's going to give you 120, right? So it gets big pretty quickly, and it has some other really nice recursive patterns. Here's another one that I'll just point out. Let's say you have k factorial, and you write down a k, and you realize, you know what, I really don't want to write down the rest of all of this. You know, let's face it. Sometimes we're a little less enthused about writing down everything that math has to that math requires? Well, here's an efficient way you can do it. What I have in the red brackets is another factorial because it's now starting at k minus 1 and it's multiplying all the integers down to 1. So I can write this as k minus 1 factorial, right? So k factorial, here's a recursive definition, is k times k minus 1 factorial. What I wrote on the first line here is the explicit definition, right? Here is the recursive definition. And there are lots of patterns, lots of uses of this that I'm pretty sure many of you will encounter in subsequent classes, right? But here's our, so for instance, again, let's write this out. Let's see what it looks like. It would be 1 to the 1 over 1 factorial. Then it would be 2 to the 2 over 2 factorial. Then it would be 3 to the 3 over 3 factorial. Then it would be 4 to the 4 over 4 factorial, and so on, right? So that's what this series of terms looks like when we write out the first few terms. Notice I put my dot, dot, dot there to show that this goes on forever. Okay, so let's see if we can write down what we need. A sub k is k to the k over k factorial. Then if I look at the next term, the term that would come after that, it would be k plus 1 to the k plus 1 over k plus 1 factorial. Now let's set up this ratio. So I'm going to do that on the other line just so that I have enough space. So if I take the next term, divide it by the previous term, and we'll start factoring stuff out. So this one, when I look at the numerator, I can write it as k plus 1 to the k times k plus 1 to the 1. And then I have my k plus 1 factorial here. So I'm going to apply this property and write this factorial as k plus 1, so that will be the first integer in my product, but then I would have k times k minus 1, k minus 2, all the way down to 1. So that would actually be k factorial. That's this. So this can be factored as k plus 1 times k factorial, and then we're going to multiply by the reciprocal of a sub k, because we have to divide by it. So I'm going to multiply by k factorial over k to the k. All right. Well, let's see. I think just a quick look, we can see several things that go away. The k factorial goes away. And we have a k plus 1 here and a k plus 1 here. So all of that goes away. And here's what we have left. We have a k plus 1 to the k in the numerator, and we have a k to the k in the denominator. And I can use my properties of exponents and write this as a single fraction all to the kth power. This is k plus 1 over k to the k. And then I can do a little bit more algebra and write this as k over k plus 1 over k all to the k, and then reduce it even a little bit further, 1 plus 1 over k to the k. All right, so that's our limit that we have to, or that's the term now. So to find our r, we're going to take the limit as k goes to infinity of what we just wrote down, the 1 plus 1 over k to the k. And if you look closely, this is one of those tricky 1 to the infinity forms, right? And we have a formula now, right? We have a formula that can be used. And I'm going to use that formula in lieu of the longer process that we, so tediously had to work through and when we're going through our Calculus 1 material. All right, so we're going to take, let me fix my K here. Take this and identifying this as A, and the coefficient of K here is also 1. So this is e to the 1 times 1. So that is e. And e is bigger than 1. So the terms of this sequence, our series, sorry, as we go far out, the ratio of the successive terms gets closer and closer to e. And because that e is bigger than 1, so since e is greater than 1, then by our ratio test, the series diverges, right? So let me go back up here. If we were to go ahead and continue this addition process and just keep adding term after term after term, we would be able to make the summation be as large as we want. So in some case, what we can say is this infinite sum is actual infinity. But the previous one that we did, example A, this one is not infinity. It's some number. I just don't know what that number is right now. But if we wanted to, we could figure it out with some more advanced math, right? Usually if you have a problem, there's some math for that. Or if there's not, there are people working on that math right as we speak. So that's our ratio test. Hopefully those two examples illustrated, the usage of it and again, how you make your conclusion. So until then, I'll see you in the next video.